you so much for the introduction. It's really nice to be here. Before I start, maybe let me just say that almost everything I'm going to talk about today is motivated by and inspired by Helen's writing and discussions with Helen, and in particular from studying her recent Springer notes on local systems, which are really, really beautiful. So I can't recommend them highly enough. So, and also everything I'm going to say is joint work in progress with Josh Lam, who's in the audience. So hopefully he'll keep me honest if I say anything wrong. All right. So what's the question that's motivating everything I'm going to talk about today? So given an algebraic ordinary differential equation, and I'll be precise about what I mean by this soon, how can you recognize when the solutions are algebraic functions? Okay, so as I'll explain shortly, for a linear ODE, there's a very famous conjectural answer to this question due to Grothendieck-Katz, the p-Curvature conjecture. But what I want to do in this talk is explain maybe some kind of version of that conjecture for a certain nonlinear ODE and some maybe modest evidence for that conjecture. Okay, so what happens for linear ODE? Well, let me start with kind of the most elementary formulation of the Grothendieck-Katz p-Curvature conjecture, and then I'll explain, I think, maybe the more standard highfalutin version of the conjecture. So this will be the conjecture for open subsets of the projective line over Q. And the conjecture is as follows. So the solutions to the ODE d dz minus a f of z equals 0, and here A is an R by R matrix. Of rational functions. So these are algebraic if and only if some arithmetic condition is satisfied. So what's that condition? So you take the operator d dz minus a. This is some differential operator. You take it to the pth power, and you ask, is this identically 0 mod p for almost all p? Okay. So this is some differential operator. Since a has rational coefficients for almost all p, you can reduce it mod p and then evaluate this differential operator on, let's say, rational functions, and then ask, is it identically 0? Okay, so the forward direction of this is pretty easy, and the backward direction is very open. All right, so this is kind of a very elementary statement of the conjecture, and it actually is equivalent to the full conjecture I'm about to write down. But to explain what's known about the conjecture, I have to give you a more general statement. So let me do that now. So here's maybe arguably a better formulation, depending on your tastes. So let's suppose X is smooth over R. I'll just put it inside of C for convenience, a finitely generated Z algebra. So what's an ODE? ODE is a flat vector bundle on X. So here E nabla will be a flat vector bundle on X, and just because I think there are some graduate students in the audience, maybe let me briefly recall what this is. So E is a vector bundle, and here nabla is a connection. So that's a R linear map from E to E tensor omega 1. Here everything is over R, so I'll suppress the notation, which satisfies the Leibniz rule.
Leibniz rule?
Leibniz rule? Is it L-E-I? Oh, okay, yeah. This is the danger of giving a talk in Europe. If I say Leibniz in the United States, no one will correct me.
You know, Liebe has a meaning as well.
I did not know that.
Lava.
Oh, okay. Well, I do love the Leibniz rule. All right. So you should think of this as a rule for differentiating sections to E. If you plug in if you have a vector field on X, you can plug it into omega, and you can differentiate sections to E. So adjointly, this gives you a map from Tx to R linear endomorphisms of E. So this is the rule for differentiating it, and it's flat if this preserves, so this map commutes with the commutator. So T is a sheaf of Lie algebras, and D is a sheaf of associative algebras, so in particular a sheaf of Lie algebras, and you want this to preserve the commutator. Okay, so what does it mean? I said this is an ODE. What are the solutions to this ODE? They're the kernel of nabla. So for example, here you can take the trivial bundle on U and take the connection d minus a dz, and the solutions to the kernel of that connection will be exactly the solutions to this ODE. Okay, and so the question is, when does E have, let me say how I have a basis of algebraic flat sections? So flat just meaning in the kernel of nabla, and okay, what does this mean? It means that that E nabla is trivialized on an étale cover of, let's say, xc. So on the generic fiber, this can be trivialized by passing to some étale cover of xc. It becomes isomorphic to a trivial bundle with the trivial connection d. And okay, then the functions on this étale cover are exactly the basis of algebraic flat sections. All right. So what's the conjecture? Again, the conjecture is some kind of positive characteristic criterion. So let me introduce the relevant notation. So given a flat bundle and characteristic P, these sheaves here have some extra structure. So here, this is an associative algebra. You can take things to the pth power. But also, if you have a vector field on a variety in characteristic P, you can take the pth power of that vector field, and that gives you a new vector field. And so you can ask, does this map adjoint to the connection respect that extra structure? And there's a way to measure that, which is the p-curvature. So if x now is over a ring R of characteristic P, you can define a map called CP, which is a map from the Frobenius pullback of Tx to end E. And what is it? Well, it's induced by sending a vector field V to differentiation along Vp times minus differentiation along the pth power of V. So this map is 0 if this map respects pth powers. Okay, and the conjecture of Grothendieck-Katz is the following. So E nabla admits a basis of flat algebraic sections if and only if this map CP is identically 0. So here, this is CP associated to, so here, CP, this is associated to E mod P, is identically 0 for here P now in U subset spec R, a dense open. Okay. So for almost all primes, when you reduce this mod P, this invariant vanishes. Okay. And maybe let me remark, there are some stronger, or at least a priori stronger versions of this conjecture. So for example, Katz has a version of the conjecture which is equivalent to this one, which characterizes the Lie algebra of the monodromy group of this flat bundle in terms of these invariants. Okay. Are there any questions about this statement? So let me just remark, maybe, if X is proper, this having a basis of algebraic flat sections has a kind of simple complex analytic interpretation. So on a complex manifold, a flat bundle is the same as a complex local system. The set of flat sections is a complex local systems. And for proper varieties, having a basis of algebraic flat sections is the same as that local system having finite monodromy. So this is a criterion for when a complex local system has finite monodromy, in terms of some arithmetic invariance. Okay.
Is that P that, is there a confusion about which P being the characteristic and P being a point here?
Oh, sorry, what was the question?
P is a point here and it's also the characteristic.
Is P a point anywhere? Hopefully not.
Element
You have
p-Curvature
Yes. Yeah, it's yeah, here I guess maybe this is a math frac P and little p is the characteristic of the residue field at math frac P. Is that okay, Carlos?
Okay. R is the confused.
Yeah, you're right that I do have two R's here. Sorry about that. All right. Well, I will abandon this notation shortly because I am about to start talking about, well, I will soon start talking about some nonlinear ODE, so there will be no flat vector bundles for a little bit. Okay, let me tell you a little bit about what's known about this conjecture before I completely abandon it. Okay, so I mean, I think it's fair to say that the conjecture is basically completely open, but there are a few cases that are known, many of them due to Len, so I'll tell you about some of those. So I think the first maybe major result on this is due to Katz, which is that the conjecture is true if this flat bundle E nabla is a Picard-Fuchs equation. So let me say what I mean by that. So there's a large source of flat vector bundles or linear ODEs in algebraic geometry. And what is it? Well, they're the cohomology of algebraic varieties. So if E nabla is equal to Ri pi lower star of the de Rham complex of y over x with its Gauss-Manin connection, where here pi from y to x is some smooth proper morphism, say. And what Katz proves is actually slightly more general than this, but let me just give you a warning. Really, you do basically need E nabla to be this full vector bundle. So we don't know the conjecture even for some ends of these vector bundles. So already that case, I think, would be extremely interesting. We know it for certain very special sum ends. OK. I think the next main case where this is known, and please correct me if I'm not getting the history right here, but I've seen this sort of variously attributed to Andrei, Bosch, and Chudnovsky. Which is that it's true if E nabla has solvable monodromy. So okay, in the original setting, maybe that's the case where A is upper triangular. So 3, this very recent beautiful work of Esnault-Groechenig which resolves the conjecture when E nabla is a rigid Z local system. So a rigid local system where the monodromy has an underlying Z structure. It's conjugate to a representation into GLN Z. And maybe let me just mention a few other of Esnault's relevant results. So Esnault and Langer proved a positive, an positive equicharacteristic variant. And Esnault and Kissen well, at least studied a version of the conjecture with a somewhat stronger hypothesis. So where, maybe I won't exactly state what they proved, but they studied a version of the conjecture where instead of having vanishing p-curvature, you have a D-module structure in characteristic P. Okay, so the question I want to talk about for the rest of the talk is, well, maybe this is some, I guess what I've said is that there's a standard conjecture for linear ODE. We don't really know that much about it, but let's make the question even harder and talk about some nonlinear ODE. And so let me ask the question, so what about nonlinear ODE And I'm not brave enough to make a conjecture for all nonlinear ODE, certainly, but I want to discuss a special class of nonlinear ODE. And just to give you an example before I make precise what I mean by a nonlinear ODE and what class, so here's an example of a nonlinear ODE that will fit into the paradigm I'm discussing. So it's the Schlesinger system, which was written down by Schlesinger in 1912, and it's the following system. So I'll say what these symbols mean. So dAI mod d lambda j is the commutator of AI and AJ for lambda I minus lambda j. So this is for I not equal to j. And here, to figure out what to do when I equals j, you say the sum over I of d AI d lambda j is 0. OK, and here, what are these AI? So here, AI from I equal 1 to n are matrix valued functions, so GLR valued functions of lambda 1 through lambda n. OK, so this is some example of a pretty nonlinear ODE. It's nonlinear because of this commutator here. And I'll explain where this comes from soon. Maybe if you haven't seen this, let me just remark that there's some parameters here. So n and r the size of your matrices and so on. So if n is 4 and the AI are instead of GLR valued, they're SL2 valued. So that's a special case. So this is up to change of coordinates, the Painlevé VI equation. So if you go on Wikipedia, you can see how people usually write down the Painlevé VI equation. It doesn't exactly look like this, but this is the form of it I can remember. OK, so maybe let me just remark, like, trying to understand algebraic solutions to these equations is not a new thing. So I don't know if Philip Bolch is in the audience, but there's been a huge amount of effort put forth, I mean, arguably over the last 100 years or so, trying to classify algebraic solutions just to this one nonlinear ODE. So it's kind of an interesting question. OK. Are there any questions about the question?
In the sum, did you want I equal to j?
Yeah, so this is the sum over all I. So I equals 1 to n.
Yeah, but you wrote j.
Oh no, this is j. So there's one of these sums for each j. So this is the point of this is that you can solve for dAI d lambda I by plugging in these expressions for all but one term.
Or maybe you should write one will be Mr. sum over AI z minus lambda I. It's isomorphic.
Yeah, I'll explain that. I'll explain that in a few minutes.
So when you say non-linear, it's still linear in the derivation. You apply derivation just once, right?
That's right. But you can always, sort of do some change of coordinates. Yeah. All right. OK, so let me say what I mean by a nonlinear ODE. It's not the most general thing I could mean, but it'll be enough for this talk. So what I'll mean is, so this is section 2. So what I'll mean is a horizontal foliation so let me say what this is and then introduce the specific class of horizontal foliations of which this will be one. The general setup will be x to s. Pi will be a smooth morphism of smooth schemes. And then the definition, so a horizontal foliation on x over s is a splitting of the tangent exact sequence, so of the sequence tx over s to tx to pi star ts to 0, which respects the commutator. OK. So what you should think of is local, at least in the complex world, locally on x, you're choosing the splitting of this map. And then, well, what is an algebraic leaf? So an algebraic leaf is a map z to x such that, well, given such a map, you get a map from TZ to the pullback of the tangent sheaf of X. And I would like this to factor through pi star TS, which I think of as a subsheaf, and I would like this to be an isomorphism. OK, so this is what it means to algebraically integrate a foliation. If you just have this factorization, I'll just say Z is tangent to the foliation. OK. OK, and then here, I guess, is a reformulation of my initial question. So given x and x, so when is there an algebraic leaf through x? OK. So because of this assumption that the splitting respects the commutator, there's always an analytic leaf. So that's, I guess, the Frobenius integrability theorem, maybe. But you can ask, when is that analytic leaf actually algebraic? Okay. So there is, as far as I know, basically one conjecture on this topic, which is along the lines of the Grothendieck-Katz p-Curvature conjecture. And that's a conjecture of Ekadal, Shepard-Barron, and Taylor. And what does that conjecture say? So it says, so if the p-curvature, and I'll say what I mean by p-curvature now, of this foliation vanishes mod p for almost all p, then all leaves are algebraic. So if you take any point, there's an algebraic leaf passing through it. Okay. So what do I mean by p-curvature of the foliation? So here, I'm going to think of my splitting is given by some subbundle f inside of Tx. So this is the foliation. It's the image of the splitting of that sequence up there. And if I'm in characteristic P, there's a map Cp of f, which goes from the Frobenius pullback of f to Tx mod f. And what does it do? Well, you send a vector field v tangent to the foliation, so a section of f, to its pth power mod f. OK, so the vanishing of this map measures whether f is preserved by this operation of taking pth powers of vector fields. OK. Are there any questions about this conjecture of Ekadal, Shepard-Barron, Taylor?
Do you want to put in the condition that the Ehresmann collection is flat at the start?
I think it's up there. I think it's just respecting the
Oh, I see. Right. It's in the algebra.
Yeah. I don't know if anyone here has seen Mary Poppins, where she flies by with an umbrella, but that's what I feel like when I'm using this hook. OK. So let me make a couple remarks about this conjecture. So first of all, I mean, this conjecture implies the classical p-curvature conjecture just by taking x to be the total space of your vector bundle. So clearly, we know almost nothing about it. I think in this generality, I'll remark there's some beautiful work by Bosch, which I won't try to summarize, but it proves the conjecture when S satisfies some pretty strong analytic conditions. So for example, if S is an abelian variety or something like that. But there's something unsatisfying about it, which is that if you have a nonlinear ODE, whether or not the leaf through a point is algebraic is really sensitive to which point you start with. Right? So for example, for the Painlevé VI equation, there's famously, I think there's 4 continuous families of solutions, 1 countable infinite family, and 45 discrete families. You should ask Philip about this if you want more details. But for a general initial conditions, the solution to this will famously be a new transcendent. So, you don't really, if you want to understand algebraic solutions to nonlinear ODE, you don't really want a conjecture that's insensitive to your initial point x. Okay, and so what I would like to do is, at least in some special cases, try to formulate a version of this conjecture which is sensitive to your initial conditions, and then improve that in some special cases. Okay. Are there any questions before I do so?
Sorry, I mean, in this conjecture, I didn't see that the end point is that the psi is zero, the zero map.
Oh yeah, sorry. Yeah, so the p-curvature of the foliation vanishes mod p. Yeah, so but crucially, there's no at x condition, right? So it's just you're just asking that this map is identically 0.
If you restrict the torsor, the group, is it equivalent to the original conjecture also?
Probably, but I would have to. Certainly for GLN, it's equivalent, but I would have to think about it. I'm not 100% sure. Which remark?
Remark.
Oh, the beautiful work by Bosch. Yeah. So he proves the conjecture if S satisfies. So that for example, if the universal cover of S satisfies the so-called Liouville condition. So, for example, if S is an abelian variety, that's what you should think. Okay, but maybe the second part of the remark was that that this conjecture is insensitive to initial conditions. Does that answer your question, or? Okay, yeah. Great. Okay, so what I would like to do is introduce. I'll state some conjecture for a special class of horizontal foliations. You can absolutely phrase the conjecture for general horizontal foliations, and maybe that's a question, but I'm not brave enough to do it. So I will only state the conjecture in the situation where Josh and I can actually prove something. So what I want to do is I want to introduce a sort of special class of horizontal foliations. So I think that's maybe section 3 of the talk, which is the non-Abelian Gauss-Modin connection. And so this is terminology I learned from Carlos, who I think was maybe the first person to write down the non-Abelian Gauss-Modin connection in general, although of course in some sense it goes back to 1912 or 1905, depending on who you ask. So this will be a class of horizontal foliations where I want to make a conjecture. Okay, so what's the setup? So x to s over R inside of C, a finitely generated Z algebra. So this will be pi, a smooth and proper morphism. And x and s will also be smooth. And okay, for this talk, I'm going to only work in the smooth proper setting, but let me just remark that everything I'm going to say can be done with a relative S and C divisor. D over S. So if you study connections with regular singularities, but I just won't say anything about this unless you ask me. Okay, so to this data, one can associate another family over S, which carries a horizontal flat connection. So what is that? That's called M de Rham, x over S to S. And what is this? This is, well, I'll write down the points. So it's triples xs E nabla, where xs is a fiber of pi, and E nabla is a flat bundle on xs. Okay, so this is some moduli stack. And I claim that this moduli stack carries a horizontal foliation over S. Okay, so there's a couple issues with making that precise, and I will say something precise later in the talk. So really what you should say is that this is a crystal over S. If you fix the determinant and only work with irreducible flat bundles, then this is a Deligne-Mumford stack, and on the smooth locus, everything I'm going to say is fine. It's literally a foliation. Okay, so I will say that this carries a horizontal foliation, and I'm putting it in quotes because I mean something slightly different. And I'll say, let me kind of tell you what, instead of describing the foliation as a splitting, let me tell you what the algebraic leaves are, or sorry, what the leaves are, so what the flat sections are. So this is given by isomonodromy. isomonodromy. So what does this mean? It means an analytic leaf is given by a family xt, et, nabla t. So this is a family of fibers carrying a family of flat connections such that the monodromy representation is constant up to conjugacy. Okay. So what do I mean by this? Well, these xt are the fibers of a smooth proper morphism. So in particular, in a family over a connected base, they're all homotopy equivalent to each other. So if you perturb xt a little bit, well, you get a homotopy equivalent space. Each of these spaces carries a representation coming from your flat bundle. And I would like the conjugacy class of that representation to remain constant. OK, so this is an analytic description. It's far from obvious that, for example, that this describes a crystalline mixed characteristic or that your foliation is algebraic, but nonetheless, that's true.
But do you know any relationships with the central leaves and tensor-free divisible groups of like the model space of abelian variety? Because they're really similar.
Yeah, I don't have anything smart to say. I would have to think about it. Yeah, maybe let's discuss it in the break. OK, so let me give you an example. So actually, I've already given you an example, as Maxime explained. But let me explain why this Schlesinger system is actually an example. Here's an example. So unfortunately, because of my decision not to include simple normal crossings divisor, it will only be a pseudo example, but the results I'm going to talk about do apply. So I want to take my base to be the configuration space of endpoints in P1. And over this, there's a pair P1 over the configuration space. Well, this is just the universal family of endpoints. And then associated to this is M de Rham of P1 D over the configuration space. So what is this? This is going to be the moduli space of flat bundles on P1 with regular singularities along D. This lives over the configuration space.
You don't specify
I don't. Yeah, I mean, it doesn't matter for this kind of thing because those stay locally constant as you flow. Yeah. All right. So yeah. So inside of this, there's the locus of Fuchsian ODE, which are flat bundles of the following form. So the underlying bundle is trivial, and the connection is given by a connection matrix with simple poles along D. OK, and on this locus, well, if you write this as so here, A is sum of AI over z minus xi dz, where the xi are your marked points, and well, this is the horizontal foliation. So that's where this example comes from. So then this isomonodromy foliation, or non-Abelian Gauss-Mann connection is this Schlesinger system. So for example, the Painlevé VI case comes when one considers 4 points on P1, 3 of them at 0, 1, and infinity, and SL2, local systems with regular singularities. All right. So let me say what the conjecture is now.
Sorry, I have some trouble understanding your notation.
Yeah.
What does P1, D mean?
Yeah, so this is over the configuration space, this universal family, which is, well, P1 times the configuration space, and then the universal configuration of points. So D is that a divisor, which is étal over this configuration space, where the fiber over an n-tuple of points is that n-tuple of points. Does that make sense for me? OK. Yeah, maybe it would help if I put D universal or something like that.
Why do you have the DZ twice? The A has a DZ.
Oh, yes, that's now, yes, thank you. The answer is because I didn't look at my notes. OK, so here's the conjecture. It's that the leaf through a point of M de Rham, so here I'm in this general setting of a smooth proper morphism between smooth varieties. And so the leaf through a point, which is, what is that? It's a fiber XS and a flat bundle, is algebraic if and only if the following holds. So the p-curvature of the isomonodromy foliation. So I'm going to write something and then explain what it means. Vanishes to order omega of p at x e nabla mod p, sorry, xs e nabla mod p for almost all p. OK, so let me say, OK, so first of all, omega of p is, this is like Knuth notation. So this just means this is some function growing faster than any linear multiple of p, than epsilon p for any epsilon. OK. So what do I mean to say it vanishes to this order? What I mean is that the leaf of the isomonodromy foliation is integral to at least this order. And when you restrict this map to that leaf, you get 0 to at least this order. OK, so let me kind of say more concretely what this actually means. So here, this is what you're supposed to think. So this is you, I guess. So if you have a foliation, you can formally integrate it using Taylor's formula. And what this really means is that the formal leaf is integral, is p integral to order omega of p squared. So when you formally integrate the leaf, you don't have any denominators divisible by p until you get to something a bit beyond p squared. OK, so this is what this really means.
We are mod p here.
So this is a characteristic 0 condition.
That's a
this is a but this is a characteristic 0 condition, which is more or less equivalent to this. It's slightly stronger than this condition.
Oh, okay.
Yeah. Yeah. This is a p-adic condition. Yeah.
What is p integral?
Yeah. So p integral meaning it's this is some formal. This is a map from a finite ZP scheme, and so and then the maximal ideal of that scheme is not killed by p squared. So it's, you have some point S in S. You look at that point p-adically. You take some omega p squared order thickening of it, and then the leaf. There's a flat section over that whole thickening. I don't know if that makes sense. There's an integral model of the leaf. Okay. Yeah. Does that answer your question?
Right now we know.
OK, great. Any other questions about this?
You want omega p squared here?
Yeah, so here you have omega p, here you have omega p squared. So for example, if the p curvature is 0, then you can integrate beyond order p, right? So there's some difference between the order of vanishing of the p curvature and how integral the leaf is, which is a value vector of p.
But do I understand correctly when you say order omega p, it means it's really the analog of p curvature for 0 and not more?
Yeah, I think it's.
You have some epsilon more.
It's so p curvature. You cannot. There's no conjecture where you just ask that the p curvature vanish at this point. So I think this is the weakest thing you can ask for. Is my feeling, but I don't know if that's. I don't know if that answers your question.
So I can imagine that denominators grow like square root of n.
Yeah, that's. I think that's how you should. Yeah. But it's not a statement about the growth rate. It's just a statement about the first, epsilon times p squared terms. Yeah.
Does this specialize to the p-Curvature conjecture?
That's a good question. So I'll discuss that in a little bit. It's closely related, as I'll explain in a few seconds, hopefully. All right. All right, so maybe let me make some remarks about the theorem and then discuss some kind, or sorry, about the conjecture and then discuss some evidence for it. Okay, so some remarks is that, first of all, as I've stated, it's imprecise. And I'll give you a precise form in a second. So the reason it's not precise is that M de Rham isn't smooth. So, and I haven't told you what a crystal is or how to define the p-curvature of a crystal, and I won't do that. But if you ask me at the break, I will. I'll give you a precise formulation soon. So imprecise as M de Rham is not smooth. And also, I mean, if you don't restrict to like irreducible local systems, it's not a scheme. Okay. So we'll fix that soon. So the observation, I think this gets at Jacob's question, which is that there's a sort of variant conjecture. So you can ask, so E nabla, if you start with a bundle, sorry, start with a point xs E nabla with vanishing p curvature, you can ask, is the leaf through this point of M de Rham algebraic? Okay. And a positive answer to this. So a positive answer would imply the classical p-curvature conjecture. Right, so in fact, a positive answer even just for x to s being the universal curve over mg. Okay. So that, I don't know if that answers your question. So there's some question, which is if you have a flat bundle with vanishing p-curvature, does it satisfy this condition? And that's not completely clear to me. If you, instead of having vanishing p-curvature, you ask for very slightly stronger conditions, it does. So for example, this conjecture implies that arithmetic D modules have finite monodromy, which I think is some natural variant of the p-curvature conjecture. Okay. And maybe let me just remark, I mean, studying the p-curvature conjecture for these M de Rhams is not a new thing. So in particular, Menzies and Papaioanou. So hopefully, I think I spelled this right. I copied it into my notes. They studied the Ekadal Shepard-Barron-Taylor conjecture. So this conjecture for M de Rham with some very interesting partial results. Okay, so I think these are some remarks. Let me, before addressing this issue 1, so making it precise away from the smooth locus of the smooth locus where the local systems are irreducible. Let me just state the theorem. So, like everything I'm going to say today, this is joint with Josh Lam. So the theorem is true if E nabla, so here we have there's some input to the conjecture, which is a triple, a fiber of our map, and a flat vector bundle. And this is an irreducible Picard-Fuchs equation. Okay. So let me say recall what this means. So this is something that appeared in my discussion of Katz's work on the p-curvature conjecture. So this means that there exists y to s smooth and proper. Sorry, y to xs smooth and proper, such that E nabla is the de Rham cohomology of the fibers with the Gauss-Monod connection. Okay. So maybe let me make a remark. So you could ask, like, how is this different from Katz's theorem? So certainly, if E nabla has vanishing p-curvature, then it's well, in this case, it's not so hard to see. I think that that's the hypothesis is satisfied. But this hypothesis on the p-curvature of the isomonodromy foliation vanishing is much, much weaker. So it's very easy to write down examples of Picard-Fuchs equations where the hypothesis of this theorem is satisfied, but not of Katz's theorem. Okay, so maybe just to give you an example, if you take any x to s and take any Picard-Fuchs equation on x, that will give you such an example. Okay, so there's lots and lots of examples. Okay. Are there any questions about this?
Do you ask for an irreducible Picard-Fuchs or an irreducible summand, for example?
Yeah, so we definitely cannot do summands. It's the same thing as in Katz. We need at least a Z structure. Yeah, so okay, this is a work in progress. My expectation is that we'll eliminate the word irreducible. I just don't want to state a theorem that we haven't written down. But yeah, so maybe just to be safe, let me say the whole thing is irreducible. Yeah, but yeah, my expectation is that for summands as in Katz, it will be fine. So if you look in Katz, he gives some kind of characterization of summands to which his theorem applies, and it should be the same characterization. And in fact, we should just be able to drop this word completely. All right. Are there any questions about this?
Yeah. So if I go back to this picture over there, if I give you some matrices AI and plug them into your conjecture, am I actually able to like put it on a computer and actually check?
Yeah. So for finitely many p, you can check, but of course it's an infinitary. It's infinitely many p. You have to check. So I think you'll never. I don't know how to find a sort of finitary condition that will prove that will conjecturally characterize algebraicity, but of course you can get very good evidence by computing up to p is 1,000.
It's even more than infinitely many.
Yeah. So in this theorem we only need infinitely many, but you're right that it's just like in Katz. So. Yeah. But it's true that in general the conjecture I would only make for all but finitely many p. Yeah. Okay. Okay, so let me say a few words to make this precise, and then I'll say a few words about the proof. But before I do that, are there any more questions? Okay. All right. So in order to make this precise, what am I going to do? I'm just going to write down a formula for the p-curvature of M de Rham. And so the statement is that if that formula is 0 to the appropriate order, then the leaf should be algebraic. And I'll also say what I mean by leaf being algebraic in a more precise way. So precise formulation. So let me just give you a formula for the p-curvature. So here, you can take this either as a definition, or if you know how to define the p-curvature of a crystal, it's a proposition, it's a computation. So what is the p-curvature of this isomonodromy foliation? Well, it starts at the source is the tangent space to the base, and the target is the tangent space to the fiber. So let me just write it down at a point. So this is a formula for p-curvature. Yeah, we're now mod p. S is a mod p point of M de Rham. So there's a Kadeira-Spencer map from the tangent space to H1 of the fiber with coefficients in the tangent sheaf. This thing lives inside of the de Rham cohomology of the fiber with coefficients in the Frobenius pullback of the tangent sheaf. Sorry, this should be a prime. So here, this is a flat bundle with the canonical connection induced by Frobenius pullback. And then, well, remember the source of the p-curvature map for a flat bundle was this vector, was f star ts. So this maps to H1 de Rham of xs with coefficients in and e nabla. So here, this is the p-curvature at the triple xs e nabla. Okay. And so let me remind you, this map is the p-curvature of e nabla. Okay, so this is just a formula for the p-curvature. And so the precise form of the conjecture is the following. So if this, so let me call this CP iso for isomonodromy. So if CP iso equals 0 to order omega p at xs e nabla mod p for almost all p. Okay, now let me give you, well, the statement should be the leaf is algebraic. Let me give you a different description of the leaf being algebraic that works in this case where x to s is smooth and proper. So then the monodromy representation of E nabla over the complex numbers has finite pi1 s orbit. Okay, so what do I mean by this? There's an action of the fundamental group of the base on conjugacy classes of representations of the fundamental group of the fiber. Well, why? Because there's an outer action of pi1 on of the base on the fundamental group of the fiber, and I would like this representation to have finite orbit. So in this case where x to s is smooth and proper, this is the same as the leaf being algebraic. I think that's a theorem of Cousin and He. Okay. And then the theorem, let me just restate it with Josh, is that this is true for irreducible Picard-Fuchs equations. Okay, so this is now a conjecture that makes no reference to things I haven't defined, like the p-curvature of a crystal. Okay, so in the last 10 minutes, I want to say a few words about the proof and some kind of related conjectures that go into it and come out of it. But before I do so, are there any other questions?
So you need, so can you say again, you need infinitely many pieces, or you need almost all pieces?
Yeah. So in the theorem, we only need infinitely many. In the conjecture, we need all but finitely many. Yeah. Yeah. But in the theorem, we only need infinitely many. Okay. So let me say a few words about the idea of the proof, and I'll just remark that I mean it's to some extent inspired by Katz's proof of the p-curvature conjecture for the abelian Gauss-Modern connection, but it's also really inspired by very recent work of Esnault-Groechenig, which I think maybe Michael will talk about a little bit tomorrow. Okay, so I think this is section 4 of the talk, which is the proof idea. So let me draw a picture. So here's x, here's s. Here's the fiber of this map, and then on this fiber we have a flat bundle E nabla. What we need is a criterion for the monodromy representation of this to have finite orbit under pi1 of the base. And so I want to explain a conjecture which gives you such a criterion, and then explain how we prove that conjecture in this Picard-Fuchs case. Okay, so the conjecture is that so here, E nabla with monodromy representation V, or associated local system V. So suppose V is of geometric origin. So here V is now some local system of geometric origin on a fiber of a smooth proper morphism. Then the isomonodromic deformation. So here this is pi to a general fiber of pi is of geometric origin if and only if V has finite pi1 s orbit up to conjugacy. Okay, so this is a conjecture. It's a prediction of the relative Fontaine-Maser conjecture discussed by Moritz in his talk. Okay, so this gives a criterion for when something has finite pi1 ss orbit. Well, if you believe the conjecture, in fact, the forward direction is pretty easy. It follows from sort of finiteness results for local systems of geometric origin. But okay, I mean, we'll never be able to prove something, some random local system is of geometric origin. You're supposed to think maybe this is some non-Abelian version of the variational Hodge conjecture or something like that. Okay, but there's a meta-conjecture. Well, you can replace geometric origin in the conjecture with any conjecturally equivalent condition. So for example, underlying a Z variation of Hodge structure. Okay. In fact, in that case, so maybe let me just remark example. So in the case of Z VHS, this is a theorem of I think Katsarkov-Pantev when S is proper, and Jost-Zwo in general, and then there's also, one can deduce it from work of Takuro Mochizuki. Okay. Okay, so how are we going to use the inspiration from this conjecture to prove our theorem? Well, we have E nabla, which is Picard-Fuchs. So in particular, it's certainly of geometric origin. We won't be able to show that when you deform it to a general nearby fiber, it's still of geometric origin, but we might be able to show that some of the features of being of geometric origin persist. So what does it mean to be Picard-Fuchs? Well, there's a few structures you get. You have a Z structure on the monodromy representation. This is obviously invariant under passing to a different fiber, since all the fibers are homotopy equivalent. You have a Hodge filtration. This carries, in fact, a Z variation of Hodge structure. Mod P, there's a conjugate filtration. Well, there's always a conjugate filtration, but it's well behaved, maybe mod P. And then finally, and this was, I think, the main observation of Katz, there's a comparison between the graded pieces. So maybe let me give the name, the Hodge filtration F and the conjugate filtration N. There's a comparison between the graded pieces of F and N up to Frobenius twist, which exchanges p-curvature with the Kadeira-Spencer map. Okay. So we know this on one fiber, and the real theorem with Josh is that so under the hypotheses of conjecture, so if this map vanishes to the appropriate order, well, structures 2 through 4 here extend to the formal neighborhood of the fiber in X. So the Hodge filtration, the conjugate filtration, and the comparison coming from Katz. Okay. So I probably will not have any time to say how one proves this. You should feel free to ask me about it in the break if you'd like. But let me just say a word about how to deduce the algebricity of the leaf. Well, this Z structure extends to any fiber for free. So what we've really shown is that on a general fiber of pi, this local system underlies a Z variation of Hodge structure. So general fiber of pi, E nabla underlies a Z VHS. So what does this imply? Well, if you unwind, I guess, the correspondence between fundamental groups and deck transformations, it implies that for all gamma in pi1 of the base, if you twist this monodromy representation by gamma, this also underlies a Z VHS. Okay, well, Deligne showed that a fixed variety only carries finitely many Z VHS with given numerical invariance. So by Deligne finiteness, this implies that the set V gamma up to isomorphism is finite, which is what we wanted to show. This monodromy representation has finite orbit under pi1 of the base. Well, that orbit is precisely the fiber of the leaf over your base. So we've shown the leaf is finite, hence algebraic. That's all I wanted to say.
Any questions?
Actually, I got lost last seconds. How I got from formal neighborhoods to...
Oh yeah, I mean there's some, yeah, right. So what we're showing is that the non-abelian Noether-Lefschetz locus, so the locus where this local system underlies a ZVHS, what we've shown is that it contains the formal neighborhood of this point in the universal cover of S. But it's some analytic closed subset, so it's everything. Yeah, so I think that's maybe in this setting, that's a theorem of Carlos.
Well, the 4 was the result of Gatwick on 1972.
Right. So exactly. So the statement 4, we know it holds on one fiber, and what we need to do is we need to show that, well, you can extend these structures in such a way that it still holds on every fiber.
Have you proved it in the compact case or in the logarithmic?
Yeah, that's a good. Yeah. So the way it's the reason part of the reason I stated this way is that what we've written is only in the case where x is smooth and proper, but I have no doubt that it will be fine. There's no. Yeah. Okay. I expect there to be no additional complications in adding regular singularities. Yeah. So it should, for example, apply to Painlevé VI.
In your conjecture for algebraicity of leaves, is there a reason why you restrict the class of horizontal foliations you consider?
Well, I don't even restrict to the class of horizontal foliations. I restrict to the class of isomonodromy foliations.
Is there a reason not to consider all horizontal foliations?
Oh, you're welcome to. I mean, I would ask it as a question. I wouldn't conjecture it because I think we have no evidence. I mean, yeah. I think it's a very natural question.
What are the other consequences of the conjecture or theorem?
Yeah, I mean, yeah. Well, so I think the main consequence is that if you can prove it for the universal curve over MG, it should imply some very slight variance of the classical p-Curvature conjecture. So that's, I mean, I don't know that you should consider this theorem to be, any progress towards the classical p-Curvature conjecture, but I mean, part of the reason that I was thinking about this conjecture is that somehow M de Rham has a lot of extra structure that you can try to use. So somehow there's, I think it gives some new perspectives to think about things relevant to the classical conjectures. So maybe that's what I would say. I mean, the way I got into this is that, Josh and I and Aaron Landsman have been thinking a lot about trying to understand algebraic solutions to things like Schlesinger systems. And so this was sort of a natural thing to try to think about.
So did you think of, of course, we always come back to this key point, which is number 4 here. And this number 4 needs geometry. I don't know of any proof of number 4 without geometry.
Yeah, I mean, we've thought about it a little bit. I think you might be able to do it if you have a Higgs de Rham flow fixed point, but I mean, it's not, yeah. So but I don't want to promise anything. I think that's, yeah. My guess is that one can probably get this 2 through 4, extend it from a fiber to a neighborhood, just with the Higgs de Rham flow fixed point. But I haven't thought about it carefully, so don't quote me.
No more questions? Let's thank our speaker again.